Picture a room in Redmond, Washington, in February 2025. A scientist named Chetan Nayak stands in front of a small metal device, no bigger than a computer chip you might hold between two fingers. He calls it a topoconductor. He says it can see and control a particle that physicists have chased for almost 90 years. He says the machine built from it could make every computer on Earth today look, in his words, like a broken abacus. Cameras flash. Reporters scramble to file stories. Within hours, headlines around the world are calling it the biggest breakthrough in the history of computing. And then, 16 months later, a single physicist in Scotland sits down with the same data Microsoft published to the world, opens it line by line, and finds something nobody wanted to find. Not a discovery, a mistake, maybe more than a mistake. The kind of thing that makes you ask a question nobody likes asking about a trillion-dollar industry. What if the breakthrough was never real at all? This is the story of that chip, that claim, and the 6 weeks in the summer of 2026, when one of the most powerful companies on the planet had to answer in public whether it had shown the world a miracle or a mirage. To understand why this story matters so much, you first have to understand the problem quantum computers were built to solve and why it has haunted scientists for over 40 years. A regular computer, the one in your pocket or on your desk, stores information as bits. Each bit is either a 0 or a 1, like a light switch that is either off or on. Every video you stream, every message you send, every game you play is, underneath everything, just billions of these switches flipping on and off at incredible speed. It works because it is simple. But that simplicity has a ceiling. Some problems are so complex, so tangled with possibilities, that even the fastest supercomputer on Earth would need longer than the age of the universe to solve them by brute force. A quantum computer tries to escape that ceiling entirely. Instead of bits, it uses something called qubits. And a qubit does not have to be just off or on. Thanks to a strange rule of physics called superposition, a qubit can exist as a mixture of both at the same time, a bit like a coin spinning in the air, neither heads nor tails until it lands. Link enough of these spinning coins together in a phenomenon called entanglement, and in theory you unlock a kind of computing power that grows not by addition but by multiplication. Add one more good qubit, the machine's potential doesn't just go up a little, it doubles. That is the dream. Here is the nightmare. Qubits are almost unbelievably fragile. A stray vibration, a tiny change in temperature, even a cosmic ray passing through the lab can collapse that delicate spinning coin before it ever finishes its calculation. Scientists call this decoherence, and for decades it has been the monster hiding under quantum computing's bed. Build a machine with too much noise and your revolutionary computer becomes nothing more than an extremely expensive random number generator. So the real race in quantum computing was never just about building more qubits. It was about building qubits that could survive long enough and reliably enough to actually be trusted. This race has been running since the 1980s, when physicist Richard Feynman first suggested that only a quantum machine could truly simulate quantum nature itself. For years, it was a theory more than an industry. Then, in 2019, Google claimed something called quantum supremacy, saying its processor had solved a calculation in minutes that would take the world's best supercomputer thousands of years. IBM disputed the claim almost immediately, arguing that, with a bit of cleverness, a classical machine could do it far faster than Google admitted. It was the first hint of a pattern that would repeat again and again in this field. A stunning announcement, global headlines, and then, quietly, months later, a counter-argument from rival scientists chipping away at the claim. Microsoft chose a different, riskier path than its rivals. While Google and IBM built their machines from superconducting circuits, and companies like Quantinuum trapped individual atoms with lasers, Microsoft bet nearly 2 decades of research on something almost mythical, a particle first theorized in 1937 by an Italian physicist named Ettore Majorana. The Majorana particle is strange, even by quantum physics standards. It is its own antiparticle, meaning if you ever brought it face to face with a copy of itself, both would simply vanish. Scientists believe that if you could capture something behaving like this particle inside a specially engineered wire and use it to build what is called a topological qubit, you would get a qubit naturally resistant to the noise that plagues every other approach. It would not need to be protected from the world so carefully. It would protect itself. It was, in theory, the holy grail of quantum computing, and it came with a history of heartbreak. In 2018, a team funded by Microsoft published a landmark paper in the journal Nature, claiming to have finally detected these elusive particles. It was hailed as a triumph. Then, in 2021, that same paper was retracted. Outside physicists discovered the underlying data had been cropped and selectively presented in a way that hid signals contradicting the discovery. The authors publicly apologized for what they called insufficient scientific rigor. For a company that had staked its entire quantum strategy on a particle nobody could directly see, it was a devastating blow to credibility. So when Microsoft returned to the stage in February 2025, it did not simply repeat its old claim. It came back with what it said was proof, and with a new safeguard built specifically to prevent another embarrassment. It called this safeguard the topological gap protocol, an automated piece of software designed to strip out human bias and stop scientists from seeing patterns that weren't really there. This time, Microsoft said, the machine itself, not human hope, had confirmed the discovery. The company published its findings in Nature once again and unveiled a working chip called Majorana 1, built on what it called a topological core architecture. It said the chip could scale to 1 million qubits on a single palm-sized device. It predicted a fully working, useful quantum computer, not in decades, but in years. The reaction was electric. The Trump administration, which had already committed $2 billion to quantum research, pointed to breakthroughs like this one as it set a national goal of a functioning scientific quantum system by 2028. Microsoft itself built an aggressive public roadmap toward a commercial quantum supercomputer by 2029. Investors took notice. Rivals took notice. For a brief moment, it looked like the company that had been humiliated in 2021 had completely rewritten its own story. But almost as soon as the applause faded, a familiar unease crept back in. Physicists outside the company began combing through the published paper, and some noticed the same kind of pattern that had haunted Microsoft before. The paper, they said, made a narrower and more technical claim than the public announcement suggested. It described software that could identify a tiny gap in an otherwise highly conductive wire, evidence consistent with a Majorana particle, but not, some argued, definitive proof of one. Sergei Frolov, a physicist at the University of Pittsburgh who had criticized Microsoft's work for years, put it bluntly. Neither Microsoft nor anyone else, he said, had laid a foundation clear enough to make these advances plausible through a series of reliable, repeatable experiments. Unlike its rivals, IBM and Quantinuum, whose progress didn't depend on capturing an unproven particle, Microsoft was still building its empire on a foundation many scientists considered unfinished. For over a year, the controversy simmered without a decisive answer. Then in June 2026, it exploded back into public view. Henry Legg, a lecturer in quantum physics at the University of St. Andrews in Scotland, published a peer-reviewed critique directly inside the pages of Nature, the same prestigious journal that had carried Microsoft's original announcement. His conclusion was devastating in its simplicity. He argued that Microsoft's supposed breakthrough rested on coding errors in a flawed version of the very topological gap protocol the company had built to prevent exactly this kind of mistake. According to Legg's analysis, basic errors in the underlying Python code had effectively manufactured signals that looked like evidence of a Majorana particle, when the raw, unfiltered data told a murkier story, one Microsoft had not fully presented to the public. Legg summed up the irony in one striking line. Last year, he said, Microsoft claimed it had built the equivalent of a precision Swiss watch. His analysis suggested that watch might never have been keeping real time at all. Microsoft did not stay silent. The company pushed back hard, disputing the validity of Legg's analysis and insisting its signal measurements were never meant to be exhaustive in the first place. It acknowledged something it called a minor off by 1 pixel bug in its data processing, but insisted this bug was inconsequential to its overall conclusions. The company also pointed out that the 2 earlier retracted papers had come from outside collaborators, and that Microsoft had not reviewed that data itself before it was published. In other words, this time was different, they said. This time, the company argued, the science was theirs, and it was sound. Here is where the story gets even stranger and even more human. Just weeks before Legg's critique landed, in an attempt to prove its critics wrong once and for all, Microsoft's team had already moved forward, unveiling an updated version of its chip. This time, they swapped the aluminum superconductor at the heart of the Majorana 1 design for one made of lead, an unusual choice, acknowledged even by Microsoft's own lead researcher, Chetan Nayak, who admitted during the press briefing that people generally try to stay away from putting lead into anything. The new claim, however, was published only as a preprint, meaning it had not yet gone through independent peer review, the very process that had just exposed problems in the original work. Many physicists, who had already grown skeptical of Microsoft's methodology, were not convinced. The pattern felt familiar. A bold announcement first, scrutiny and skepticism second, and an uncomfortably long wait before any real independent confirmation arrived, if it arrived at all. To understand why so many scientists reacted with suspicion rather than celebration, you need to see the bigger picture, because Microsoft's story was not happening in isolation. It was happening inside a field with a growing trust problem. In March 2025, a separate team of researchers published a paper in the journal Science claiming they had used a quantum computer to calculate the behavior of a complicated system of qubits, a feat they said was simply impossible for any classical computer to match. It was celebrated as yet another landmark proof that quantum machines had crossed into territory ordinary computers could never reach. Then, more than a year later, in May 2026, researchers at the Flatiron Institute in New York quietly dismantled that claim. Using clever new mathematical tools, they showed that a classical computer running on ordinary hardware could in fact tackle that same supposedly unbeatable problem. One of the researchers, Joseph Tyndall, admitted that whenever his team sees a headline claiming something is impossible for classical computers, their first instinct is always skepticism. Ask what wasn't tried, he said. Ask what wasn't tested. Even more revealing was a paper that had struggled for years just to be published at all. A team led by physicist Sergei Frolov, the same skeptic pushing back on Microsoft, set out to replicate some of the most celebrated quantum computing results in the field. Instead of confirming breakthroughs, they found that many of the signals once hailed as major advances could be explained by much simpler, much less exciting physics. Their paper took a staggering 2 years of review before finally being published in January 2026, a delay that highlighted just how uncomfortable the scientific community had become with publicly questioning its own celebrated breakthroughs. So, was the biggest quantum computing breakthrough ever really fake? The honest answer is more complicated and more interesting than a simple yes or no. Nobody has accused Microsoft of deliberate fraud. What critics like Henry Legg and Sergei Frolov are describing is something more familiar to anyone who has ever chased a dream too hard. A pattern of interpreting uncertain, noisy data in the most exciting possible light, wrapping it in confident language, and rushing it in front of the world's cameras before the slower, more boring process of independent verification could catch up. It is the difference between lying and believing too quickly in your own miracle. And yet, strip away the controversy for a moment and remember why any of this matters at all. If a stable, scalable quantum computer is ever truly built, whether by Microsoft's topological approach, or by a rival's superconducting circuits, or by trapped ion machines, or by some technology not yet invented, the impact would ripple through nearly every corner of modern life. Pharmaceutical researchers could simulate the exact folding of a protein in seconds, a process that currently takes supercomputers weeks, unlocking new medicines for diseases we cannot yet treat. Chemists could design entirely new materials atom by atom on a screen before ever mixing a single compound in a lab, accelerating everything from better batteries to more efficient solar panels. Logistics companies could solve optimization problems so complex that today's computers can only approximate the answer, saving fuel, time, and money across global supply chains. And perhaps most unsettling of all, a sufficiently powerful quantum machine could one day crack the encryption that currently protects almost every secure message, password, and financial transaction on Earth, which is exactly why governments like the United States are treating this race not just as a scientific curiosity, but as a matter of national security. That is the stake sitting behind every press release, every disputed paper, every retraction. Billions of dollars in private investment, billions more in public funding, the reputations of some of the most respected scientists and companies on the planet, and a technological prize so enormous that the temptation to announce victory just a little too early may be almost impossible to resist. So where does this leave us, standing here in the summer of 2026, staring at a chip called Majorana 1, a rebuttal to the rebuttal, and a brand new lead-based prototype still waiting for its own turn under the microscope of peer review? The truth is, nobody outside a small circle of physicists yet knows for certain whether Microsoft's topological qubit is a genuine scientific milestone, an honest but premature conclusion, or a beautiful idea still waiting for evidence solid enough to support it. What we do know is that science, when it works the way it is supposed to, does not collapse under scrutiny like this. It survives it, or it corrects itself because of it. Every retraction, every peer critique, every uncomfortable Nature comment is not proof that quantum computing is a fraud. It is proof that the system built to catch fraud, and honest mistakes alike, is still doing its job. Somewhere in a lab right now, in Redmond, in Santa Barbara, in Scotland, in a dozen countries racing toward the same impossible machine, someone is running a new experiment, checking old data one more time, or writing a single line of code that could either confirm a miracle or quietly unravel one. The next great quantum leap, when it finally comes, and if it finally comes, will not announce itself with a single triumphant press conference. It will arrive the way real breakthroughs almost always do, tested, doubted, retested, and only believed once every skeptic in the room runs out of objections. Until that day, the race continues, the claims keep coming, and somewhere between the dream of a computer that could reshape medicine, security, and human knowledge itself, and the fragile, flickering particle that may or may not truly exist, the future of computing hangs, quite literally, in superposition, both possible and impossible, both real and unreal, until the moment the world finally, undeniably, watches it collapse into truth.